So let's look at what we can do to make this initial force or initial impulse that we're applying to the pegs be a little more accurate when our ball doesn't hit them head on. Now if we were to think about our collision, let's think about a situation where our ball doesn't hit our peg straight on. Maybe it kind of hits at an angle like this. Obviously taking the ball's velocity and applying it directly to the peg would make your peg move straight down like this, and just intuitively this seems wrong. What we really want to do is have our peg kind of move out at this sort of angle. And it turns out that this vector that we want to sort of launch our peg on initially is equal to basically the vector that describes the relationship between our ball and our peg. This is what's called the normal vector of our collision. And I believe this normal vector really just points from the center of one shape to the center of the other shape. And kind of intuitively we can tell this just seems to be the better initial vector that we want to be using for our collision. So let's go back to our code and make this happen. So maybe the first question is, can we easily calculate this normal vector from our ball to our peg? And it turns out we can. We can do this easily from our Puggle contact listener. It turns out this B2 contact point that gets passed on to our function not only contains a reference to shape 1 and shape 2, it contains some other useful information about our collision, including normal. And this normal basically means the normal vector. And by the way, in case you're wondering how I figured some of this stuff out, it's not like I'm actually much of an expert. I actually just kind of looked at the source code, and you can do this easily in Flash Develop. If I move my cursor onto B2 contact point, and I hit F4, that jumps me to the source code that defines this thing. And here you can kind of take a look and be like, oh, look, here it looks like it's calling the position of where the contact happened. And this normal here, it looks like it points from shape 1 to shape 2. Well, gosh, that's exactly what we're looking for. So if you're ever kind of in doubt or wondering how something works, don't be afraid to kind of go in there and look at the source code. It's pretty well documented. They did a pretty good job of commenting it. Just don't try and change anything. But anyway, back to our contact listener. So we notice that our normal points from shape 1 to shape 2. And so it looks like probably what we can do is not when we pass in our linear velocity and our mass, we can also pass in the normal. And that will describe the initial angle that we want our peg to launch itself off of. So let's try that. So let's go back to our peg actor, and within my set collision info function, in addition to accepting the ball velocity and the mass of the ball, I can also accept the collision normal vector. Now your first impression might be, well, okay, we've got our collision normal. Can't we just replace our ball velocity with our collision normal and get this all to work? Almost, but not quite. The issue that you run into is that I believe collision normal is always a unit vector. That is, it's always a vector of length 1. And I think we still want the initial velocity of our peg to be somewhat proportional to the velocity of our ball. So what I can do is my force to apply, we can initially set it to our collision normal, and we can multiply it by our ball mass, but then we should also multiply it by our ball velocity's length. And at this point, actually, I think this should work. Let's just make sure we're passing it in properly, and we can test it. All right, so let's go back to our Puggle contact listener. And we just have to make sure we pass in the normal of our collision as our third argument. So now you might be tempted to just write point.normal here. However, remember that point.normal points from shape 1 to shape 2. And in this case, shape 1 is our peg actor, shape 2 is our ball actor. And really, we want our peg to start moving in the direction from the ball to the peg. So I actually need to get the opposite of this point normal. And I suppose there's a few ways I can do it. I'm just going to kind of do a quick and dirty way and create a new B2 vec2 that's made up of the point normal x times -1 and the point normal y times -1. However, over in this second part of the function, where shape 1 is our ball actor, shape 2 is our peg actor, and we really want our initial force to be from shape 1 to shape 2, we can just pass in as our third argument point.normal. So let's save this and run it and see how it all looks. Well, initial impression is it seems pretty natural. Let's do what we did before and kind of hit this thing at just an off angle and see what happens. Well, all right, that looked a little better. Did you notice when I kind of hit the ball to the side, it jumped to the left instead of going straight down? That's definitely a lot closer to what we want. So that's pretty good. However, if you are a stickler for physicsy details, there are even further refinements we could make from here. After all, if you want to get super technical, yes, the initial direction that we want our peg to move is equal to the normal vector, or the normal between the ball and the peg. The problem is that right now we're not modifying the strength of that initial force. Our peg moves just as much from a head-on collision as it would from sort of a little nick like this. And again, I think intuitively you can kind of get that if we just nick our peg, a smaller amount of force should be applied than if we were to, say, hit the peg head-on with a ball of the same velocity. And okay, yeah, we could calculate this if we wanted to. Really, in a case like this, our force should equal our force times the cosine of theta, where theta happens to be the angle between the ball velocity and our collision normal. In other words, take this little angle here, this is theta, take the cosine of that, and that's going to be a number between 0 and 1 that we could apply to our force. And you know what? I'm not going to walk you step by step through all this because at this point, I think we're getting diminishing returns here, and we've kind of spun out on this a little too long already. However, if you're interested in seeing the math, this is what it looks like. I can go ahead and pause this so that you can check it out and try it out on your own later if you're so inclined. And if you're not so inclined but you want to see what it looks like, it looks a little something like this. Not a very subtle difference, but you are maybe noticing in places where I just kind of nick the peg. It's getting pushed off in a particular direction, but it's getting pushed off in a particular direction at a much smaller force than it was previously. So there you go. This is, I think, our final treatment of making our pegs turn into real moving objects once they get hit by the ball. But this was an awful lot of steps to get there, but we did learn some important things along the way, like the danger of talking to strangers and how to apply forces using apply force and apply impulse. And by the way, I didn't really mention it, but one of the strengths of using apply force or apply impulse instead of set velocity is it works on objects that are already moving. Box2D does all the calculations for you. So at this point, I don't know if there's a whole lot left. Let's just spend the next lesson covering the remaining things that might be on our to-do list.